right? So we mentioned these two types of indices, ordered index and hash index. In ordered index, we are having search keys. Those are stored in sorted order. In hash index, we are using some hash function, and the hash function takes the input as the search key, produces some address, and accordingly these records are being uniformly distributed throughout the buckets or blocks. Further, we talked about the index evaluation metrics. Right? So in index evaluation metrics, we have discussed about access type. So what kind of query we are dealing with. Second is the access time. So access time is the time it takes to find a particular data item using the technique that we are using. Next is the insertion time. So what is insertion time actually? It is the time it takes to insert a new data item, and this time includes the time it takes to find or locate the correct place to insert the new data item, as well as the time it requires to actually insert the data and the time it takes to update the associated index structures. So this is called as insertion time. Similarly, we are having deletion time, and also we are having the space overhead. So based on these 5 criteria, these 5 metrics, actually the index under consideration is being evaluated, right? And depending on the application and the metrics those we are considering, we make a decision which index to be used, right? So now today we are going to extend our discussion related to ordered indices. So as we have stated, in an ordered index, index entries are stored sorted on the search key value. For example, if we go to the library and if we look at the author catalog, then the author catalog is ordered according to the names of authors, right? So in an ordered index, index entries are stored sorted on the search key value. So we are having actually two kinds of indices under this category. Those are known as primary index and secondary index. So we are going to talk about both these categories, primary index and secondary index. So what we mean by primary index? If the file is sequentially ordered, then the primary index is an index whose search key also defines the sequential order of the file. I'll repeat, if the file is sequentially ordered, then the primary index is an index whose search key also defines the sequential order of the file. So what we mean by that? Let me give you one example. Suppose we are having the instructor file. In instructor relation, we are having the attributes like ID, name, department name, and salary. Right? Now, let us assume that this instructor file is ordered sequentially as per this attribute ID. I repeat, I'm having this instructor relation with 4 attributes, and we are assuming that this instructor relation is ordered sequentially, and the order that has been maintained to store the instructor records is based on this attribute ID. So instructor file is sequentially ordered based on this ID. So I am having, say, instructor ID 1, 2, 3, 4 and so on. So ordered according to ID. Right? Now, if the file is sequentially ordered like this, then the primary index is an index whose search key also defines the sequential order of the file. So in my primary index now, if I am going to create the primary index for this instructor, then this primary index also uses ID as the search key. Are you getting me? Yes, are you getting me?
Yes, ma'am.
Okay, so I'll be giving one more example. See, for example, if my instructor relation is ordered sequentially as per the name of the instructor, right? So my instructor table is ordered according to name of the instructor. So I'll be having instructor name, say starting with A, then AB, then maybe B, C, and so on. So instructor file, instructor relation is ordered according to the attribute name. In this scenario, my primary index would have the search key, which is the same as the attribute according to which the instructor table is ordered. So if I am creating the primary index for this instructor relation, then the instructor relation is ordered according to attribute name. So my primary index is having search key, which is name. Right? So whichever is the actual order of records that is stored in the relation, the same attribute is being used to create the primary index for that relation. Now, this kind of primary index is known as clustering index also. So the synonym for primary index is the clustering index. And the search key of a primary index is not necessarily the primary key of the relation, not necessarily, but it may have, right? So always it is not the case that the relations are ordered according to the primary key. So for instructor table, the primary key is ID. But not necessarily the instructor table is ordered according to ID. It may happen sometimes that the instructor relation is actually ordered according to the name of the instructor. So in this situation, my primary index search key will become name. If instructor relation is ordered according to the primary key, that is ID, then my primary index will include search key as ID. So it depends. So this statement is really very important. The search key of primary index is usually, but not necessarily, the primary key. It may be any attribute. according to which actually the records are ordered in our file. Right? So I hope you must have understood what we mean by primary index. Now let us proceed to the other kind of index, and that is the secondary index. So an index whose search key specifies an order different from the sequential order of the file is known as secondary index. So meaning, say for example, if my instructor relation is ordered according to the sequential order of name, my relation is ordered according to name of the instructor, right? But if I'm using creating the index based on the search key ID, then this is called as secondary index. I'll repeat. The instructor relation is actually ordered according to name of the instructor, right? But the index is using some other attribute to prepare the index. Say for example, instructor relation is ordered according to name and the index is having the search key, say ID. Then this order is with respect to attribute name and this order is with respect to attribute ID. So these two are different attributes. So indexing attribute is different and the actual sequential order of data is with respect to different attribute. Then such kind of index is known as secondary index. It is also called as non-clustering index. Fine. So let's proceed with one more definition. Indexed sequential file. So ordered sequential file with a primary index on the search key is known as indexed sequential file. What does this mean? Say for example, if I am having the instructor table, right, and it is ordered according to say attribute ID and I am having a primary index. So once again the search key for primary index is ID. Then this instructor file is known as the indexed sequential file. Right? So ordered sequential file with a primary index on the search key is known as the indexed sequential file. Right? So let us proceed now. An index record or index entry. As we stated earlier, the index record or index entry consists of a search key value along with one or more pointers. Those are pointing to one or more records with that value as their search key value. Right? So what I mean by this, see for example, if we are having our instructor table, I am having ID, name, department name. Right? Now, if ID is the primary key for this instructor table, right? So I am having a single record with one unique ID. if I'm creating the index for this instructor relation with search key as ID, then my index record will include this search key value, say ID 1, 2, 3, along with a single pointer that points to that particular record with this ID. So associated, this is my index file. So what I'll be having in my index file? I'll be having the search key value. Let us assume the search key value is ID. Along with this ID, I'll be having a pointer. So search key value and the pointer. So if I'm having the instructors with ID 1, 2, 3, 4 and so on, then in my index, I'll be having the records for these IDs 1, 2, 3, 4 and so on. And I will be having the pointer that points to this particular record having this search key value. So associated with this search key value 1, I'll be having the pointer that points to this record 1. So let us assume that this address is P1. So I'll be having pointer P1. For this 2, suppose this address is P2. So associated with this 2, I'll be having the pointer P2 and so on. So in this situation, as I'm having the unique record with respect to the search key value, I'll be having a single pointer. Right? But in several situations, suppose now my instructor table is having these 4 attributes, okay, and I'm creating the index on, say, department name. So index is being created based on department name. So what I will have in my index? I will have search key value is department name, right? And the pointer for the record. So how many departments I'll be having? I'll be having one entry in my index for each unique department. Say for example, we are having CSE department, we are having mechanical department, we are having physics department, and so on. So these departments are ordered, right? Because I'm creating index on department name. But now in this scenario, I may have more than one records having this search key value CSE as department name. Do you agree with me? Yes?
Yes, ma'am.
So if I'm creating the index based on department name, then my search key values are the various departments, those I'm having. But I'm having more than one records for each department. So in my index associated with this value of department name, say CSE, suppose I'm having 3 records. Those belong to CSE department. Since 3 instructors, those belong to CSE department. Then I need to store all those pointers, say P2, P3, P4. These 3 instructors belong to CSE department. So here I'll be storing the set of pointers along with this department name CSE. Right? So an index record or index entry consists of a search key value and pointers to one or more records with that value as their search key value. Right? So if I am having the unique record for every search key, then I'll be having a single pointer. But if I am having more than one records for a search key, then I'll be having those many pointers. Right? Are you getting me?
Yes.
Yes, ma'am.
Fine. So the pointer to the record actually consists of the identifier of the disk block where that record is stored. And also it consists of the offset within the disk block to identify the record within that block. So my pointer consists of a disk block identifier, so disk block ID, along with the offset within that disk block. So whenever we are, say suppose I am referring to this index, right, and I want to go to, say, the record with ID 3, then I will search ID 3 in this index file first, and I will look at the pointer associated with this search key value 3. Suppose I am having here this pointer P3. So what this pointer P3 includes? This pointer P3 includes two important components. The first is the disk block, where that particular record, instructor record with ID 3 is stored, right? And as we have seen, in one block we are having several records. So first, this will take us to the disk block where the record is available, and further in pointer we are having the offset also, where actually that record is stored within that block, right? So this is how actually the pointers are being stored in our index file. So I hope you must have understood the concept. May I proceed?
Yes, ma'am.
Fine. Now, let us see types of ordered indices. So we are having two more types, dense index and the sparse index. So let us see what we mean by dense index and what we mean by sparse index. Okay, so let us first see what is dense index. Suppose this is our instructor relation with four attributes: ID, name, department name, and salary. Right? Now, if I am creating the index such that every search key value appears in my index, then I will say that this is the dense index. See here, the search key value is ID. So I am having all the IDs. So all the search key values along with a pointer. So in dense index, index record appears for every search key value in the file. And that is why it is called as dense index. For every search key value, we are having the record in index file. Got it? Yes?
Yes, ma'am.
Fine. So we have seen what is dense index. Now let us see what is sparse index. So see this figure. So once again, this is the instructor relation and we are having four attributes: ID, name, department name, and salary. Now, if we look at this index, this is my index, right? And the search key for this index is ID. So see here, how many different values I am having for my search key ID. But in sparse index, every search key value is not included. Rather, very few search key values are included to create an index. Right? So, sparse index contains index records for only some of the search key values. And this kind of index is applicable when records are sequentially ordered on search key values. So if the order of my search key in index and the order in which I have stored the records, if both are same, then only such kind of sparse index is applicable. So see here, this instructor record is sequentially ordered according to ID. And I am creating the index on the same attribute ID. So in this case, I may come up with a sparse index wherein I will not be including all the search key values, but I will be having few of the search key values in my index. So this is sparse index. In dense index, we are having all the entries, all the search key values in our index file. Whereas in sparse index, we are having only few search key values in our index. So let us see now how actually in case of sparse index, how the record is being located having some search key value k. In case of dense index, we are having every search key value in our index along with the pointer. So there is no issue. We may directly jump to that particular location referring to the pointer stored in the index file and we may find the record. But in case of sparse index, we are not having all the search key values stored in our index. So how to locate a record with search key value say k? So what we are going to do is we are going to follow two steps to locate a record with search key value k using the sparse index. So what we are going to do is, first of all, we are going to find out the index record with largest search key value which is less than or equal to k. K is the record that, or k is the search key for the record that I want to locate. So what I will do, I will refer to my sparse index and I will find out the index record with the largest search key value which is less than or equal to the key required. So once I locate that index record, then I will be following that pointer. And then I'll be searching my file sequentially, starting at the record to which the pointer has pointed. What does this mean? Let us see this example. So once again, we are having here the instructor table, right? And this is my sparse index. So search key value is ID. So in my sparse index, I am not having all the search key values. Now let us assume that I want to search a record with search key value k is equal to say 45565. I want to search a record with search key value k is equal to or ID equal to 45565. So ID is my search key here. Okay, so what I will do, I will refer to my sparse index. So this is my sparse index. Okay, so I'll be finding out the index record with largest search key value that is less than or equal to k. So my search key value that I am looking for is 45565. So I'll be looking for the ID here, the largest search key or the largest ID which is less than or equal to this 45565. So I will find this particular record in my index file. So 32343 is the largest ID which is less than the ID 45565. Right? So I have searched this record in my index now. So associated with this index record, I am having this pointer, and this pointer is taking me to this particular record having this search key 32343. Right? So what I will do next is I will search now sequentially from this point onwards. Okay, so I will search now whether this search key is 45565. No. Whether this search key is 45565. No. Whether this search key is 45565. Yes. So from the pointer that I have followed, I have reached to this record, and from this record onwards I'll be matching the ID with my search key value, and I'll be sequentially searching from this record onwards, right? And I'll be able to find out whichever is the record that I wanted, right? So this is how the sparse indices work for searching a record in a file. Now, obviously, as we are having very few entries in our sparse index, this kind of index requires less amount of space. So, dense index requires more space than the sparse index. And also, the sparse index is having less maintenance overhead. Less maintenance overhead for the operations like insertion and deletion, right? Because as the index is sparse, it is not the case that for every insertion and deletion of a record in a file, the index gets updated. Sometimes only the sparse index gets updated, otherwise no. So less maintenance overhead for insertion and deletion. Whereas if we are having the dense index, for every insertion and deletion, we need to update the dense index records. Right? I hope you must have understood this concept. So, if we compare now the sparse index and dense index, once again, in terms of how fast it will locate the required record, then obviously the sparse index is slower than the dense index. Obviously. Why? Because in dense index, I am having every entry in my index. Right? So I can search for that record and I can directly jump to a particular record. In case of sparse index, what happens is we are having very few entries in our index. So whenever I'll be directed to one of the records in my actual relation, then I need to sequentially search the required record with the required search key value sequentially in that particular file. So obviously the time required to search a particular record in case of sparse index is more. And that is why we are saying that generally sparse indices are slower than the dense indices for locating the records. But a good trade-off is usually the sparse index is being maintained for every block in the file corresponding to the least search key value in the block. So we are going to look at this concept in a short while, right? So what usually is being done is a sparse index is being created such that in sparse index we are having the least search key value in a particular block. So one entry per block we will be having in our sparse index, and that entry will contain the least search key value. Right? We are going to look at this concept in great details in a while. So I hope you must have understood the discussion so far. Right? So let us go to one more concept, and that is known as the multi-level index. So what we mean by multi-level index? Obviously, as the name suggests, we are having multiple levels of indices instead of having a single level. So what does this mean and why such kind of multi-level index is being required? So sometimes it may happen that the index file itself becomes very large. The index file itself is becoming very large. What we mean by that? Say for example, we are dealing with a huge database or a relation having billions of records. In those billions of records, we are having billions or thousands of search key values. Right? So, if I'm maintaining, say for example, the dense index, or even if I'm maintaining the sparse index, comparatively many index records I will be having, more index records I will be having in my index file, because my data itself is too big and the search key values are also many in number. So I'll be having a big index file having lots of search key values along with the pointers stored in that index file. So sometimes it may happen that my index itself is too large, and if I'm having my index file too large, then once again it is not efficient for processing. Ultimately, the indexing mechanism is being used to expedite the access to the desired data. So obviously, we are aimed for searching the data quickly. And if my index file itself is too big, then once again, it impacts on the efficiency of processing. Right? So, example so that we can understand this concept better. So let us assume that our file is having 1 lakh records with 10 records stored per block. Let us assume that we are having a file which includes 1 lakh records with 10 records stored per block. So obviously, how many blocks are required to store 1 lakh records? If I'm storing 10 records per block, then how many blocks are required to store 1 lakh records? Yes?
10,000.
10,000 blocks. Right. So, to store 1 lakh records, I will require 10,000 blocks, assuming that every record requires fixed size. Right? So, with this assumption, the number of blocks required to store these 1 lakh records is 10,000. Let us assume that we are having one index record per block. We are creating the index such that we are having one index record per block. Then my index will have 10,000 records because I am having 10,000 blocks. So one index record per block. So in my index, I will be having 10,000 records. Correct? Are you getting me?
Yes, ma'am.
Right. Now, as we stated, the index record requires small amount of space than the actual data record. Right? So let us assume now to store this index file. So obviously I am having the index file with 10,000 records now. Okay, now let us assume that one block contains 100 index records. Actual data records, one block, 10 records. Now, index records are much smaller than the actual data records. So, we are assuming that one block now contains 100 index records. So, once again, this index file is also stored onto the blocks, and this index file is having 10,000 records. So obviously this 10,000 records we need to store onto the blocks. Now let us assume that one block contains 100 index records. Right? So obviously to store my index file, I will require 100 blocks. Because every block is storing 100 records, I am having 10,000 records to store. So obviously, to store my index file itself, I will require 100 blocks. Right. So now, you must have understood this concept. My index file is too big now, and to store this index file itself, I'll be requiring 100 blocks. Right? So, such large indices are actually stored as sequential files, and to search for an entry, it requires now several block reads because the index is being searched sequentially. So if my index file spans over 100 blocks, and if I need to read the index sequentially, obviously to locate a particular record, I need to search all those index records sequentially. So obviously I will require more time. I will require more block reads. Right? Even though I go with binary search, because we know that binary search is more efficient than sequential search. So even though we prefer to use binary search, then if my index occupies B blocks, then my binary search requires log of B to the base 2 block reads. Meaning, if I am having 100 blocks, right? So for 100 block index, I'll require log of 100 to the base 2. That means 7 block reads on an average. Right? So if we assume that a single block read requires 30 milliseconds. This is assumption. If one block read requires 30 milliseconds, then if I want to read 7 blocks, then obviously my search will take 210 milliseconds. To search for a particular record, I will require approximately 210 milliseconds. So 210 milliseconds is significantly large amount. Right? So I'm taking long time to search for a particular record, even though I am using binary search. Right? And this is not acceptable in modern systems where we are very much interested in finding, in locating, in searching, in accessing the data immediately in fractions of seconds or milliseconds rather. Okay, so to cope up with this problem, we are having the multi-level index. So if primary index does not fit in memory, access becomes expensive. Right? So if my primary index does not fit in memory, then access becomes expensive. Right? So what we are going to do is to reduce the number of block accesses, we are going to treat our primary index, which is stored onto the disk, as one sequential file. And we are going to construct a sparse index on my index file itself. Right? Say for example, see here in this figure, this is actually my index file. So in our example, our index file was using 100 blocks to store index records. So I'm having these 100 blocks over here. Right? So this is my primary index, wherein this primary index file is stored in 100 different blocks. So what I will do is, I will treat this index file as one sequential file that is being stored onto the disk. And I will try to create the sparse index on this index file itself. How I'm going to do that? See here, these index records are sequentially stored in these 100 blocks. So I'm having block 0, block 1 and so on. So I'm having such 99 blocks wherein I have stored my index. So what I will do is, I will create one more index like this. Right? So this is the index file. Now I'm treating this index file as my data file, which is sequentially ordered. And for this sequential ordered index file, I'll be creating one sparse index, such that in my sparse index, I'll be having one entry per block. So see here, I'm having this entry for this block 0. I'm having second entry for block 1. I'll be having third entry for block 2 and so on. Right? So in my sparse index, I'll be storing one entry per block. And what I will have in this sparse index, I'll be having the same search key value, but if this is a block, whichever is the least search key value in this block, block 0, that least search key value is being stored here along with a pointer that points to that particular record. So whichever is the least search key value in block 1, that will be stored in this sparse index. Right? So why we are saying this is sparse index? Because every search key value is not being stored. Right? So we are saying that this is my inner index wherein I am having the primary index file, and this is my outer index wherein I am having a sparse index for this primary index. If even this outer index becomes too large to fit in our main memory, so it may happen that even though we have created this sparse index on the index file, then it may happen sometimes that this outer index itself becomes too large and this index cannot be accommodated in our main memory. So what we can do is we can go with yet another level of indexing. Right? So what will happen then? This becomes my inner index now, and I am having one more level of index that is called as outer index. So once again, see here, this sparse index is being stored now onto the disks. So let us assume that this sparse index also is too large. So it also requires many number of blocks, right? Then what we can do is we may come up with one more level of index. So in this outer index, what I will have? Once again, the similar strategy. So this sparse index is being stored onto the blocks. So one entry per block will be there in this outer index. So the first entry in this block, the first entry in this block will go here in this outer index, right? So as per requirement, we may add more than one levels of indices for efficient access to our data. May I proceed?
Once again, repeat, ma'am.
Okay. So what we mentioned is our data actually is large and data is stored in say 10,000 blocks, right? We have created the index, primary index on this data, and my index file itself is now once again too big, and to store the index file I require 100 blocks, right? So this is my index file. So to store the index values I require 100 blocks, right? And if I am looking for some data, how many data records I am having? I am having say 1 lakh records, right? And I want to locate one record out of this 1 lakh records. So obviously I am having this index file with me. So I will be referring to this index file, but this index file also is stored onto 100 blocks. So if I want to look for a particular record in my data of 1 lakh records, I need to sequentially search in this index file. So one block after another. So every record I need to look for. Do you agree with me?
Yes, ma'am.
Right. So if I'm sequentially searching this index file, then it is time consuming. Even though I'm using binary search, then also I will require significant block reads. To avoid such large time to access different blocks or to minimize the block reads, what we are going to do is we are going to have one more index for this index file itself. So now this index file is being treated as our data file. So this index file is having 10,000 records. This index file is stored in 100 blocks. So what I will do is I will create one sparse index to locate the records in this index file, because I do not want to search sequentially. So what I will have is I will have one record per block in my sparse index. So if I'm having 100 blocks, then in my sparse index, I will be having 100 records, one record per block, right? So sometimes once again it may happen that even though we have created this one more level of index, to store this sparse index, I'll be requiring many number of blocks. So once again, if required, it is possible for us to add one more level of indexing. So once again, we'll be treating this sparse index as our data, and for this sparse index, I'll be having one more index, wherein once again, this is a sparse index, and once again, I'll be storing one entry per block. Right? So this is how we are going to maintain the multi-level indices for efficient access to the data. Right? And please note that indices at all levels must be updated. If we are inserting some data or we are deleting some data from our file. Getting me? Cleared the
Yes, ma'am.
doubt? Cleared the doubt?
Yes. Yes, ma'am.
Fine. So let's proceed now for the operations those we are performing on the database and the respective changes those we need to carry out with respect to the index file. So we'll be going through these updates or the operations like insertion and deletion and how it affects our index files, and then we'll conclude this session. Right? So let us see now the index update. So operation under consideration is the insertion operation. So what we are trying to do, suppose I am having this instructor table with 4 attributes, say ID, name, department name and salary. Okay, now if I want to insert some record in this instructor table, let us assume that this instructor relation is sequentially ordered according to the ID of the instructor. Right? So these are the IDs. that we have in this instructor table. If we want to insert a new record, let us assume the index is being created with search key value ID. Okay, now if I want to insert a record in this instructor relation, what I will do? I will perform a lookup using the search key value appearing in the record to be inserted. What we mean by that? Suppose I want to insert a record with search key value 8. Search key value is ID here. Suppose I want to insert a record with search key value 8. So what I will do is, first of all, I will look for the search key value 8 in the index. Right? And while inserting the record, now I need to consider where my index is dense index or whether my index is sparse index. In dense index, I'll be having each and every search key value in my index. In sparse index, I'll be having few search key values. So let us assume now that we are having a dense index associated with this instructor relation, meaning whatever are the search key values right now present in our instructor table, I am having all those search key values in my index file as well, associated with a pointer that actually points to that particular record. So this will point to this will point to this, and so on. So I am having one pointer associated with that record. Now, as we are talking about the dense index, what will happen if the search key value does not appear in the index? So what I want to insert instructor with ID 8. So what I will do, I will look for that search key value in my index. Right? So this is being searched sequentially. Let us assume. So 1, 2, 3, 4, 5. So 8 is not there in my index, meaning that record is not available here. I'm inserting a new record. Right? And I'm not having that search key value present in the index. So what I will do is, I will insert that search key value at the appropriate position. So I'll be inserting here that search key value 8 after 5 and before 10. Right? Now, what next? Otherwise, meaning if the search key value is present in my dense index. Now, let me give you another example for this. Suppose once again I am having instructor table, but now my search key for instructor table is, say, department name. Right? And here I am having the dense index with search key value, say, department name. And I am having, say, for example, 3 departments: CSE, mechanical, and physics. Right? So as this is dense index, all the search key values, all different search key values are present. Right? But here, if I am having this dense index and if I look at the pointers, I am having more than one entries, those belong to CSE, or more than one entries, those belong to mechanical, and so on. Right? So if I am inserting a record with ID equal to 8 and department equal to CSE, then what will happen? I will search in this index this search term, that is CSE. right? So I'm having that record available, CSE. And here I'll be having set of pointers. So those pointers are pointing to the respective records of CSE department, right? So if my pointer is storing the pointers, or my index record is storing the pointers to all the records with the same search key value, then what I need to do? As this CSE is available, but I want to insert a new instructor from this CSE department, what I need to do is simply I need to add a new pointer that points to the new record that I'm going to insert in this instructor relation. Right? So I need to update my index such that I need to add a pointer that points to the new record in my instructor. Right? Sometimes it may happen that if my instructor relation is ordered according to department name, then all the records belonging to the CSE departments are stored in a contiguous way. So in this situation, what will happen? The index record do not store all the pointers, but instead my index record will store a pointer that will point to the first record of CSE department. Right? And the system will place the record in this bunch of CSE department. So if presently I am having 3 records from CSE department, and if I am trying to insert a new record of instructor from CSE department, what will happen? First, it will check my dense index. I'll be having the CSE entry there. I am having only one pointer pointing to the first record of CSE department. And I have stored all the records from CSE department in contiguous manner. So I am having all these 3 records one after another. So this pointer will take me to the first record. Then I will go to the last record of CSE. I'll insert here the 4th record from CSE department. And I need not update here anything. Right? Why? Because already the pointer contains the address of the first record from CSE department. Got it? So in this situation, I do not need to update my index. Correct? But if I am having now, suppose a new record to be inserted, and this new record to be inserted belongs to, say, zoology department. And I do not have data from that department yet. So obviously in my dense index, I will not have that department listed. So in this situation, I need to add one record in my dense index which stores the department name as zoology, and along with that, it will store a pointer that points to the new record that I have inserted in my instructor table. Right? So these are these different situations how our index gets updated at the time of inserting the data into a file. So please remember, whenever we are inserting a data in our relation, obviously if we are having the associated index, that index also needs to be updated. And this updation process depends upon whether the index is dense index and whether the index is sparse index. So right now we talked about the dense index. So what if my index is sparse? So if my index is sparse, meaning I'm not having all the search key values stored in my index. So let us assume now that my index is storing one entry for each block of the file. So suppose I am having the instructor data and this instructor data is being stored in different blocks and I am having a sparse index. And in this sparse index, what I will have? I will have one entry per block. Right? So if the new record is, we want to insert a new record, then what will happen with respect to this sparse index? If the new record has the least search key value in its block, then the system updates the index entry pointing to the block. Otherwise, no change to the index. What does this mean? Say for example, suppose we are storing in one block, suppose we have stored 1, 2, 3 up to 10 instructors. So instructor ID is 1, 2, 3, 4 up to 10. So 10 records are stored in one block. Right? Now, suppose in this block, I am storing 12, 13 and so on. 10 records. So this is the sequential order that is being maintained while storing the data onto the blocks. Now, in my sparse index, what I will have? The least ID, the least search key value from this block. So it is 1, along with the pointer to this record. Here, the least search key value is 12. So I'll be having in sparse index this 12 and the pointer and so on. Okay. Now, if I'm inserting a new record, let us assume that I want to insert in one block only 10 records are accommodated. Okay. Now let us assume that I want to store a record with ID 11. So obviously there is no space here. So it will go to the next block and here I want to insert the new record in this block. Right? And while inserting in this block, the record that I am going to insert is having the least search key value. So in this situation, what will happen? My sparse index will get updated such that the least record will be inserted here in this block at the first position and this sparse record or rather sparse index gets updated such that the search key value will be 11 and the pointer also will be pointing to this record 11. If I'm storing the instructor record with search key value 15, right? So this block will be located to store that record and there is room to store the record in this block. So there is no need to update this entry of my sparse index. So this is what we mean by this first condition. Right? Now, in other situation, if my block is full, then if my block is full, I need to create a new block. And if I'm creating a new block, then the first search key value appearing in the new block needs to be inserted in my sparse index. Right? So, if I'm creating a new block, I need to add a new entry here in my sparse index and accordingly I need to update this pointer as well. So this is how actually the insertion operation is performed by updating either our dense index or our sparse index. Have you understood the concept? So you may once again go through all those different conditions, right? So that you can understand it better. Right? So we are considering two kinds of operations, insertion and deletion operations in data. So whenever we are performing insertion operation or whenever we are performing deletion operation, the respective changes in index also need to be performed. So our index file also need to be updated. So depending on the type of index that we have, whether it is dense index or whether it is sparse index, accordingly we need to take the actions with respect to the current insertion of data. So we have seen several different possibilities for updating our index, right, with respect to different cases. So I would appeal all of you to once again go through this discussion after this session so that you can clear your concepts. The similar kind of operations we need to perform whenever we are dealing with deletion operation. So while deleting one record, we need to locate the record, and after locating the record, the next action depends upon the type of the index that we have. So once again, if it is dense index, then obviously we are having every search key value in our dense index, right? And if we are performing deletion operation, then we may come up with several cases. So if the deleted record is the only record in the file with a particular search key value, then the search key needs to be deleted from the index file as well. Otherwise, that means this is not the only record having that search key value. So we are having several records with the search key value. Then what needs to be done? If the index record stores pointers to all the records with the same search key value, then the system deletes the pointer to the deleted record from the index. Right? But if my index is storing only the pointer to the first record with the search key value, and if the deleted record is the first one, then only we need to once again update our dense index. Otherwise, we don't. Right? So similarly are the cases for sparse indices. So you should go through all this discussion once again while dealing with this insertion and deletion operations. Right? So I hope you must have understood the concepts of primary index, secondary index, right? Those are the categories of ordered indices, and further we have seen the dense index and the sparse index, and the operations those we may perform on the index file while performing the insertion operation and the deletion operation, right? So I hope you must have understood the concepts those we discussed. If you have any doubt, please let me know. Otherwise, we are going to conclude the session. Is there any doubt? Yes? Is there any doubt?
No, ma'am.
Fine. So in the next class, we are going to focus upon the secondary indices, right? And few more details regarding these ordered indices. Okay, so let's conclude today. Thank you.